This is the second video in a small series discussing how MRI works, delivered in a timely fashion. If you haven't seen part 1, you should really watch that first or you may get lost here, link in the description. In this video, I'm hoping to go a little deeper into Boltzmann magnetism and our magnetic moment ensemble, the NMR experiment, and the effects of inhomogeneous magnetic fields. This will all lead us to the primary topic of the video, the spin echo. On our last episode, we discussed the basics of the NMR phenomenon, including precession, T1 and T2 relaxation, and the signal equation following a 90-degree pulse. Then we asked the question, what is Boltzmann magnetization, M0? Well, we touched on it last time, but never actually defined it. Instead, we examined a related quantity, the polarization, which describes the fraction of spins which contribute to NMR signal. So let's see how polarization and magnetization are related. So continuing with where we left off in the last video, Boltzmann magnetism, or magnetization, is the equilibrium nuclear magnetization of a spin sample in a magnetic field. Every proton has the same magnetic moment mu, which is equal to gamma, its gyromagnetic ratio, times h bar, the reduced Planck's constant, times its spin quantum number, which in the case of protons is 1/2. As we know, our sample is composed of a great many protons, each with the same magnetic moment. Boltzmann magnetism is simply the vector sum of all these magnetic moments when they're in equilibrium. Of course, in the absence of a magnetic field, these spins lack a defined orientation, but in the presence of a magnetic field, these spins orient themselves in one of two possible states, spin up or spin down. The spin up state, where the spin is aligned with the field, is the low energy state and is thus preferred, but as we saw in the last video, the energy difference is so small compared to the temperature of the sample that the spins are nearly equally distributed between these states. Only a few spins out of every million are in excess in the spin-up state. In the last video, this led us to a discussion of polarization, the fraction of spins which are in excess in the aligned low energy state, which we saw simplified to this expression for samples in thermal equilibrium. As a reminder, this polarization is the spin's gyromagnetic ratio gamma times the reduced Planck's constant h bar times the external magnetic field strength B0 divided by 2 times Boltzmann's constant K times the sample temperature T in Kelvin. We were able to work this out directly using concepts from Boltzmann statistics, again link in description for a refresher, but then we just kind of stopped without actually defining Boltzmann magnetism. But here's a bit more detail to help out. If we want to actually calculate equilibrium magnetization of our spin sample, like we said, that should just be the vector sum of our magnetic moments. Since we know that the spins exist in only two states, up or down, we know every pair of up and down spins will result in a net cancellation of magnetization. Thus, only the unpaired spins contribute to a sample's nuclear magnetism. And now we can intuitively write an expression for Boltzmann magnetism. It's simply the magnetic moment of a single spin times the number of spins that we have in our sample, then times the polarization, the fraction of those spins which are unpaired. So plugging in these values, we find the total magnetization of a proton sample in a magnetic field B0 is given by this expression. We often compile all these terms into a single variable, chi0, which is the static nuclear susceptibility of a sample. It essentially tells you how big of a magnetic moment you'll get in a given magnetic field strength, and it is inversely proportional to temperature. So this is called the Curie law, after Pierre Curie, husband of Marie Curie. As we've said a number of times, Boltzmann magnetism is the nuclear magnetism of our sample in thermal equilibrium, so I find myself using those terms interchangeably. Boltzmann magnetization, equilibrium magnetization, same thing. If you want to test your understanding a bit further, work out the units of this expression. Does it match the SI units of magnetic moments? So with this foundation, I'm going to abandon the energy state picture of nuclear magnetism and replace it with a single vector representing our Boltzmann equilibrium magnetization. Since we always align the z-axis of our frame of reference with the magnetic field B0, our Boltzmann magnetization vector is created along the same axis. Any NMR experiment essentially involves knocking our sample's magnetization out of equilibrium, whereupon it delivers detectable signal as it returns to Boltzmann equilibrium, the signal we detect and analyze. So here I'm illustrating an NMR experiment where we might knock the nuclear magnetism out of alignment with the B0 field by a flip angle theta. The key to understanding NMR dynamics is that our magnetization vector will return to Boltzmann following the relaxation principles we discussed in the last video. Its transverse magnetization will decay to 0 at the T2 rate, and its longitudinal magnetization will return to Boltzmann at the T1 rate. Because of the precession phenomenon, the amount of our magnetization in the transverse plane dictates the amount of signal we detect, which we saw last time increases as the precession frequency omega increases. And thus, we report an expression describing NMR signal of a sample. The signal is proportional to the number of spins in our sample times the magnetic moment of an individual spin, times the fraction of those spins contributing to the NMR signal, times omega, which is gamma B0. Notice the effect our magnetic field strength has on our detected signal. Let's say we double our external field strength B0. What happens to our signal? It quadruples. Remember, for samples in thermal equilibrium, there's another B0 buried in the polarization expression. Increasing our magnetic field increases our precession frequency and our Boltzmann magnetism. Thus, signal is proportional to B0 squared. Neato, huh? Note, however, that if our sample is not in thermal equilibrium, such as in hyperpolarized gas MRI, then the expression we derive for polarization no longer applies and our signal will scale linearly with field strength. Before moving on, all of these magnetization dynamics are typically summed up into a tidy expression called the Bloch equation, named after Felix Bloch, pioneer of NMR. I'm not going to go into the details about it here because there's other stuff to do, but it would be remiss not to at least mention such a fundamental equation here. In a future video, we'll build and solve the Bloch equation, but in its simplest form, it says that in the presence of a magnetic field B, a magnetization vector M will precess about B in a sort of conical trajectory whose cone angle is essentially twice the angle between B and M. In the meantime, try working the math out for yourself. Okay, this may be a good time to clarify something. On the last video, I drew this ball and arrow representation of a proton, which I think helps to conceptualize the spin magnetic moment, precession, flip angle, and relaxation phenomena. But just to clarify, individual protons can exist only in one of two Zeeman states within a magnetic field, spin up or spin down. The dynamics we're examining pertain to ensembles of many protons. For example, the longitudinal magnetization in our sample, i.e. the magnetization pointing in the direction of our field, is actually representative of the number of protons in each state. Higher if more spins are in the spin up state, negative if more spins are in the spin down state, and 0 if there's equal numbers of spins in each state. Thus, longitudinal magnetization returning to Boltzmann equilibrium is simply the return of spins to their equilibrium state populations, which we saw was contained within the polarization equation. The signal detected during precession is the energy released during state transitions. For those familiar with electronic energy transitions, which occur in fluorescent lamps and lasers, this nuclear energy transition follows nearly identical quantum mechanics. The difference is that the energy separation of the two states is proportional to the external magnetic field strength, B0, as opposed to just atomic structure. So, we'll do a proper video of NMR quantum mechanics later, but for now we'll stick with the tried and true classical description. So from now on, I will use a single arrow vector to describe nuclear magnetization vector of our spins within a particular space. Okay, so the simplest NMR experiment we can devise is to place a sample of spins in a magnetic field B0 and deliver a separate magnetic field B1 perpendicular to B0 about which the magnetization will precess. In a reference frame which rotates at the Larmor frequency of our magnetization M in B0, the B1 pulse is stationary. In the laboratory frame of reference, the B1 pulse rotates at the Larmor frequency, as does the magnetization M. When our magnetization has been rotated, say 90 degrees, it's entirely perpendicular to the static B0 field, maximizing our detectable signal during its precession. We then detect the resultant free induction decay as the magnetization works its way back to Boltzmann equilibrium. This is often called a ping experiment or pulse acquire. Note that my vector cartoon is showing the rotating frame picture, right? So it's animated in a frame of reference that rotates at the Larmor frequency. But my transmit and receive plots here show both the rotating frame signal in white and the laboratory frame signals in yellow for transmit and cyan for receive. We'll discuss the mathematics behind transitioning between rotating and laboratory frames later, but for the curious, this is most often achieved electronically by simple heterodyning, like a radio. Oh, and notice that my rotating frame cartoon shows B1 along the x-hat axis, which excites our magnetization into the y-hat axis. Turns out you can precisely deliver B1 pulses along any direction within the rotating frame's xy plane, and thus place M along any direction you'd like. In order to do this, you need to take note of the phase of the Larmor oscillator. The phase of the oscillator within your excitation pulse will dictate the excitation axis for your magnetization, and thus the phase of your detected signal as well. If we look at our cartoon immediately at the point in time following delivery of our B1 pulse, we can see that the choice of laboratory frame phase in our pulse diagram dictates the precise alignment of our B1 field within the rotating frame and thus the detected signal. In the ping experiment, it may not seem like that matters too much, but we'll see later that many NMR and MRI pulse sequences are designed to leverage this fact, especially in cases of multiple B1 excitations. So just keep that in mind as we move forward. So in order to perform this NMR experiment IRL, you need to go to the NMR physics store and buy yourself an NMR, a device which can deliver these excitation pulses and display the acquired signal on your oscilloscope. So you prepare a sample of plain water, plenty of protons, i.e. hydrogen nuclei, to examine. You place your sample in a strong magnetic field B0 and wrap the sample with wire, which will be an RF coil for transmission of excitation pulses and subsequent reception of NMR signals. The NMR is plugged into your oscilloscope and you window the display to show 1 second of received signal because you know from a simple Google search that the T2 of water is about 1 second. So you're expecting the received signal to look something like this. After 1 second, the signal will have decayed to about 1/E, or 37% of its initial value. In exhilarating anticipation, you execute the ping sequence, and you get this. You triple check your equipment, you read all the manuals, retry the experiment, but for some reason, the NMR signal you detect decays much, much more quickly than you expected. Why does your signal decay so fast? Perhaps your water sample is contaminated with minerals which are reducing its T2? Or perhaps the internet was wrong when it said water has a T2 of about 1 second? Well, it actually turns out there's an assumption we've made throughout our tour of NMR which is now being challenged. Our B0 field isn't perfectly homogeneous. We've assumed that B0 at every point in space is exactly the B0 field strength in the z direction. But of course no field is so perfect, and even slight variations in the field strength and direction can have a substantial effect on our NMR experiments. Consider 2 proton spins. One experiences a B0 field of 1 Tesla, and the other experiences a B0 field of 1.000001 Tesla. Exactly 1 microtesla higher than his buddy. Given that the gyromagnetic ratio of protons is 267.5 times 10 to the 6th radians per Tesla, that's 42.6 megahertz per Tesla, how long will it take before these spins are 180 degrees out of phase with each other and thus will produce no NMR signal? Pause the video to work it out if you'd like. So this difference in B0 leads to a difference in omega following the Larmor equation. The difference in B0 field is 1/millionth of a Tesla, and thus the difference in frequency is 267.5 radians, or 42.6 revolutions or hertz, which means that the spin in the higher field will complete 42.6 more precession cycles than the first every second. The spins will therefore be pi radians, or 180 degrees out of phase, in 11.7 milliseconds. A difference in magnetic field of 1 part per million reduces the coherence of spins down to milliseconds. This is what's happening in our NMR experiment. Tiny imperfections in our magnetic field homogeneity can have a dramatic effect on our detected signal. This is a problem, because now the rate at which our signal decays does not reflect the properties of the sample. It reflects the external conditions of our experimental setup, namely how good or bad of a magnetic field we can produce. So last time, we saw that the signal decays at a rate t2 due to spin-spin interactions. But when relaxation due to field inhomogeneity is considered as well, our observed signal decays according to a new time constant which we call T2 star. That means our ability to contrast tissue is substantially reduced. So now what? Can we fix this? Oh, and you might also be thinking, wait a minute, we saw in the last video that spins will only experience excitation if the frequency of our B1 excitation pulse is matched to the spin's Larmor frequency. Well, if the spins are in a different field strength, then they have different Larmor frequencies. Could you still excite both spins with a single frequency B1 pulse? I guess their Larmor frequencies are close enough. What if the second spin was in a B0 field of 1.001 Tesla, a part per thousand off? If you're thinking along those lines, good! We will absolutely examine all those intricate details of excitation in a later video. For now, we will assume all spins' magnetic moments experience excitation, even if their Larmor frequencies are not exactly equal. So let's explore this a bit more closely in our sample of spins here. I'll draw a single plane of spins to make it easier to see, but note that of course spins exist in the full 3D space of our sample. I'll go ahead and add a coordinate system to orient ourselves. We'll begin with the spin sample, which is initially in equilibrium with a magnetic field pointing in the positive z direction. That is, they're all at Boltzmann magnetism. We'll work in the rotating frame here. Remember, this means we spin ourselves around at the Larmor frequency, so from this perspective, the spins do not precess about the B0 field, which essentially means I won't animate the spin's precession about the z-axis. Okay, let's deliver our B1 excitation magnetic field in on the negative y-axis. So our spins then precess about the B1 field, and when they are perpendicular to the B0 field, i.e. at a 90-degree flip angle, we turn off the B1 field. Now the total magnetization of our spins is in the positive x direction of the transverse plane and thus delivering detectable signal. So let's think about the dynamics of their subsequent dephasing and T2 decay. I'll orient the camera so the magnetic field is coming out of the screen here, and I'll also add another vector here to represent the magnetic moment vector sum. As we said in the last video, the randomly distributed spins are experiencing the external B0 field of our magnet, but also the magnetic fields of each of their neighbors. If we try to describe this for a single spin, we would say its precession frequency omega sub k for the kth spin is equal to the Larmor frequency plus some delta omega, which of course is just gamma times some delta b. And remember, even though I'm not animating it here, the spins are also bouncing around all over the place by Brownian diffusion, so the delta b here can fluctuate in time as well. This delta b is what causes our spins to dephase and our transverse magnetization to decrease over time. The T2 decay we all know and love. Now we're working in the rotating frame, right? Which means we're spinning our frame of reference at omega 0, and thus we drop the omega 0 term here. The spins only exhibit precession in this frame if their delta omega is non-zero, clockwise if it's greater than 0, and counterclockwise if it's less than 0. So let's get our magnetization plot ready and play the animation. Hopefully this seems familiar from the last lecture. The spins dephase and total magnetization decreases following e to the minus t over t2. Rotating frame's kind of nice, isn't it? Conveys all the information we need without making me dizzy. Now most textbooks will illustrate this using a stacked view of the spins rather than a messy image of all the spins all over the place. Since the NMR coil is assumed to detect all spins with equal sensitivity, this illustration makes perfect sense and is much cleaner to visualize, especially for our upcoming discussion on echoes. So let's put our total magnetization vector back in and play the T2 animation. This fanning out of spins represents T2 decay, which is manifest in the reduction of the magnetization vector length over time. So with this picture available to us, perhaps we can develop a mathematical expression for the total magnetization vector m. This shouldn't be too bad, right? After all, the magnetization m is just the vector sum of the individual magnetic moments mu sub k. Okay, so what is mu sub k? The vector describing the kth magnetic moment. Well, it's probably easiest to describe in terms of its frequency omega sub k. If we do that, we can see that the x component of mu is cosine of omega sub k times time, and the y component would be minus sine of omega sub k times time. So that makes sense, and it suggests that if omega is positive, mu will precess clockwise in this orientation, which is indeed how spins with positive gyromagnetic ratio like protons precess about magnetic fields. Well, I don't know about you, but whenever I see cosine and sine arranged like this in a vector expression, I immediately think of Euler's relation. With this, we can abandon the Cartesian x hat and y hat expression in favor of real and imaginary axes. Thus, I can express my vector as a complex number, e to the minus I omega sub k t. This is so much cleaner, because complex numbers, by design, contain two pieces of information, real and imaginary, in a single expression, with the added bonus that rotations are much easier to describe mathematically. If you're not used to doing this, I would encourage you to give it a try next time you're dealing with rotations or sinusoidal motion. It truly makes life much easier. Now, with each moment being mu times e to the minus I omega t, we express our transverse magnetization in time as such. Note that in this model, the individual spin magnetic moments all have the same magnitude. This makes mu a constant here, so we can pull that out front. Now, summing over omega sub k isn't super helpful unless we know what all the mu's frequencies actually are. Well, what we can do is examine the distribution of spins with a given frequency. That is, the number of spins which have a given omega, kind of like a histogram for omegas, but since it's continuous, we call it a frequency distribution. Oh, and the title omega frequency distribution is not redundant. This is a frequency distribution of omegas. Yeah, anyways, maybe it looks something like this. Most spins are pretty darn close to an omega of 0, which in the laboratory frame would be the Larmor frequency. Some spins are a little faster, some are a little slower, but as we get farther and farther away from omega equals 0, the number of spins with those frequencies goes down substantially. I wonder what kind of distribution this is. Well, it really doesn't matter. The point is that this distribution, f of omega, describes how many spins have a given frequency. There are f of omega 1 spins with frequency omega 1. Omega 2 would have f of omega 2 spins, etc., etc. So we can just rewrite our sum over k omegas as a sum over all omegas, where e to the I omega t describes a particular spin frequency, and f of omega is how many spins we have at that frequency. Now, of course, we're dealing with septillions of magnetic moments over a continuous spectrum of possible frequencies, so this sum is really an integral. And we have the result that our magnetization as a function of time, and thus our detected signal as a function of time, is just mu times the integral over all frequencies omega of the frequency distribution times e to the minus I omega t d omega. OMG. This is the definition of the Fourier transform of the frequency distribution f of omega. This means that the rate at which our signal decays in time reflects the distribution of frequencies our spins possess, and vice versa. The way I drew this frequency distribution here was not an accident. It's called a Lorentzian distribution, and we'll do a deep dive into the actual math in a later lecture. But my dear friends, Fourier theory is the mathematical foundation of MRI. Truly, you cannot say you understand how MRI works if you can't also say you know how a Fourier transform works. For some of you, the beauty of seeing a Fourier transform appear here makes perfect sense, and you probably saw it coming from miles away. But perhaps for others, just the phrase Fourier theory incites feelings of dread and panic. Fear not! The next video in our journey through MRI will be dedicated entirely to what the Fourier transform is and how it works. Until then, let's just develop a conceptual understanding here. A sample of slowly dephasing spins demonstrates a corresponding slow decay of magnetization and a narrow frequency distribution, showing a relatively tight grouping of spins near omega 0. Compared with more rapid dephasing, let's say, and a quicker decay. So this forms the basis of T2 contrast weighting, which we saw last time. Now, because we know that omega equals gamma b0, we know our omega distribution is actually indicative of a distribution of regional magnetic field B, since all protons have the same gamma. This distribution of the magnetic field strengths experienced by our spins dictates our FID decay. So, returning to our picture of many spins in space, we know that each spin experiences some delta B due to the tissue environment, but also some delta B due to our imperfect field. So to help us visualize, I'm going to show the magnetic field in space as a color map. Spins in the purple region experience a slightly lower field, and spins in the red region a slightly higher field, with a full range of delta B in between. The Larmor equation tells us that the field and homogeneity will broaden our frequency distribution, thus reducing our decay time. So instead of placing our spins on a field color map, I'll just color each spin according to its experienced field strength here. And now we can stack them up and observe the accelerated dephasing. We'll use this stacked picture again in a minute, but let's walk through the math a bit. Immediately following excitation, all our spins are aligned in the x direction, and we have a macroscopic ensemble moment to detect. If our spins were all at the exact same frequency, our signal would never decay, and our distribution would be perfectly narrow. And our signal in time would just be a constant. But of course, our spins do dephase due to intrinsic molecular dynamics of our system or tissue. Our signal is thus modulated by e to the minus r times t. R is the decay rate and is characterized by time constant t2, which we've seen before. Our signal thus decays, and our distribution widens. Now we have another source of decay, so our already decaying function gets a second modulation term, e to the minus rb times time. Rb here is the decay rate due to the field and homogeneity. The nice thing about exponentials is that the decay constants multiplying time just add, and we can write a decay rate r star comprehensive of all sources of spin dephasing. R star by this model is clearly just equal to 1 over T2 plus R sub b, which we can write as gamma times delta b, which is just delta omega. Similar to T2, R star can be characterized by its own time constant, which we designate T2 star, which is the observed signal decay rate due to all the dephasing mechanisms present in our sample. So as we've said, this is problematic for us because our new signal decay is more representative of our magnetic environment, not molecular properties intrinsic to tissue. Thus, our ability to contrast tissue in an image is drastically reduced. To illustrate this, consider 3 tissues of various T2s and equal Boltzmann magnetizations. Here are their T2 decay plots in a perfectly homogeneous field, where delta B is equal to 0. At an echo time of, say, 40 milliseconds, we can contrast tissue very well. If our field and homogeneity increases to just 1 part per million, our observed decay time T2 star is reduced to milliseconds. Not only do we have to acquire our signals much faster, but our ability to contrast tissue is dramatically reduced, if not gone depending on our signal-to-noise ratio. Best case scenario, we'd be imaging a tissue with infinite T2. That would drop this term out, but notice we can't do any better than 1 over gamma delta B. And this part per million example I keep using does indeed reflect most commercial MR scanner limits. Manufacturers boast field and homogeneity about 1 part per million within the volume of the scanner bore. Of course, field homogeneity gets better as you image a smaller and smaller volume. Fields can be 10 to 100 parts per billion if your field of view is down to tens of centimeters, which is quite impressive, but of course is a large percentage of a scanner's price tag. But it's important to remember that even if you can manufacture a magnet with absolutely perfect field homogeneity, once you put something to image inside, especially living physiologically active tissue, the field will be distorted and delta B will increase. So you can only go so far perfecting a field anyways. Oh, and you might have noticed that somewhere along our discussion we made a jump from having a frequency distribution describing our field and homogeneity to a single number delta B. What happened there? Shouldn't it be, some sort of integral or something? Well, it so happens that if we model our distribution using the Lorentzian line shape I mentioned earlier, delta B can in fact be represented by a single number. This number is most often related to the Lorentzian's full width at half maximum or half width at half maximum, depending on which textbook you read. In our Fourier theory video, we'll develop the relevant math, but for now, rest assured this is a common mathematically sound practice. Okay, quick recap. The ping NMR experiment involves exciting nuclear magnetization into the transverse plane, where its transverse decay reflects our detected signal and intrinsic properties of the tissue. But because our field is imperfect, the decay is accelerated and our ability to contrast tissue is reduced. We're about to discuss a revolutionary method for reversing the effect of field and homogeneity on our FID. But before we do, can you think of a way to get our spins back in phase after dephasing due to field and homogeneity? Perhaps a cartoon of the color spins dephasing might help. Pause the video if you'd like to ponder your own solution. Well, consider the NMR experiment. I'll draw our signal plot here and I'll use these pink bars to indicate excitation pulses. Of course, the 90-degree pulse knocks our magnetization out of the longitudinal plane and into the transverse plane so we can detect the FID. A simple yet clever idea was suggested by Felix Bloch and first experimentally verified by Erwin Hahn. Just deliver a second pulse. We'll deliver this pulse soon after the FID is decayed and we'll make it a 180-degree pulse, as was suggested by Carr. Can you predict what might happen to our detected signal? Here's our 3D magnetization vector cartoon to help. So as expected, the FID is seen following the 90-degree pulse. But the addition of the 180 results in a signal echo of sorts. This is called the spin echo. So what just happened? Well, let's return to our dephasing spin cartoon to help. The B0 field is coming out of the screen here, and I'll add our signal plot for us to follow. Remember that the spin colors represent their associated external field strengths. Red is in a high field, purple in a low field. Notice what the 180-degree pulse does to our dephased spins. After they're rotated 180 degrees, their precession continues, but they eventually rephase with each other. We can deliver another 180 if you'd like. The result is another echo. Notice that after the 180, the spins continue to precess at a rate dictated by their field strength and represented by their color. Purples in the low field are always precessing counterclockwise. Reds always clockwise. The 180-degree pulse doesn't change where the spins are in space, and so does not change their precession frequency. Perhaps this is easier to see if we look at the animation of the spins unstacked. If you want, you can focus on an individual spin to verify that its precession frequency does not change following excitation. The spins dephase, then following the 180, they rephase into a peak and then continue to dephase. There's two important things to notice about the plot that I've drawn here. First, you might notice that the dephase-rephase parts of the plot seem to be mirrored around the 180 pulses. Second, you see that our echo peaks get smaller in time. So what's going on? So as we've seen, the detected FID follows T2 star decay. If we deliver our 180 at a time tau, then in that time, the spins will have dephased by a certain amount. We should therefore expect that following the 180, the spins will take exactly that amount of time to rephase. The echo peaks decay because, unlike dephasing due to field inhomogeneity, intrinsic T2 decay is not reversible. Spins are still losing coherence due to their self-interactions. Here I'll draw the plot of T2 decay. Notice that our peak comes right up to the T2 plot. And in fact, this is the take-home. If our 180 is delivered at time tau, the echo will appear at a time 2 tau, and its peak will reach the T2 decay curve. Thus, the peak amplitude can be used to calculate T2. We've regained our T2 contrast. Notice, by the way, that while I animated the B1 pulse on the rotating frame's x-axis, echoes will appear regardless of the excitation axis. Here's an example with B1 at 45 degrees to x. We still get an echo, but it appears along the y-axis. Thus, we can expect our echo to have a different phase as our FID, just like we saw earlier. I'll simplify the animation here with just a few spins to illustrate the effect of delivering B1 at different orientations in the rotating frame. Notice the green spin does not precess here. His delta B is 0. He's perfectly at Larmor resonance. As such, we know all his buddies will align with him at the echo. We can use this fact to help with our discussion. Here's my dephase spins immediately before 180. Notice the angle our green spin makes with respect to the B1 field. Following the 180, our spin will be at this angle on the other side of B1. Thus, we can expect our echo to be at twice the phase of our B1 pulse relative to the magnetization vector. Okay, so why does this work? Well, the reason is that our spins have acquired a certain amount of phase at time tau following the 90-degree pulse, and the 180-degree pulse effectively reverses or negates this phase accumulation. So let's examine a spin with a negative gamma here so that the angle theta of our spin would just be positive omega t, which is a little easier to work with in the argon plane. The real component mu x reflects cosine omega t, and the imaginary component mu y reflects sine omega t. These components can be visualized on a single plot and imply a counterclockwise progression in phase, as per the negative gamma. If we deliver a 180-degree pulse along the x-hat axis, the imaginary component becomes negative, but the real component is unchanged. This takes our sine omega t and makes it negative. The reversal of the imaginary component mathematically switches the phase we've accumulated from positive to negative, minus theta. Our system will continue to evolve, progressing in phase counterclockwise at rate omega t. The total accumulated phase will thus be 0 when our time t equals tau, and we'll detect an echo. Pretty neat, huh? The math is nice and simple here, where B1 is aligned along the real axis, but perhaps you can extend the math for cases of B1 delivered at an arbitrary angle to the system. Oh, and here's a leftover spin echo animation in the laboratory frame, just so you can visualize what's going on. I only am showing one of these here because it makes me dizzy, and it doesn't really help the discussion much. Oh, so there you have it. The spin echo. While we focused on dephasing due to field and homogeneity as being reversible by the spin echo, it will also reverse dephasing due to chemical shift and heteronuclear spin interactions. Spin echo sequences in MRI do have some drawbacks. They're often rather long sequences to conduct, and they do involve much more RF delivery compared with simpler gradient echo sequences, but we'll examine all those details at a later time. But now you know the story of how helpless NMR signals are freed from the prisons of inhomogeneous magnetic fields by the humble 180-degree refocusing pulse, thus allowing for true T2 contrast. If you really want to put your newfound knowledge to the test, try a few of these exercises. Post your solutions in the comments, see if others got the same answers, and have fun. That concludes part 2 of our little MRI intro, and thank you for watching. And sorry it took so long to deliver. I do intend to continue this little intro series. The next video will be all about Fourier theory and the Fourier transform. Fourier theory is so ubiquitous in science and engineering that another YouTube lecture may just be a drop in the ocean, but it's so fundamental to studying MRI that I can't not make one for the MRI Fundamental series. I'm thinking 4 videos total in this intro series, with the 4th being a discussion of how gradients produce images and the gradient echo pulse sequence. After that, we'll be well positioned to discuss MRI topics in detail without leaving anyone behind. Things like pulse sequences, MRI hardware such as spectrometers and coils, chemical shifts, hyperpolarization, clinical MRI, reconstruction and acceleration techniques, etc., etc., etc. Maybe you have a question or topic you'd like to see. Post a comment. I'm definitely not a full-time YouTube person, so I simply don't intend to respond to every comment like some of the greats do, but if I do see questions and a lot of people give them thumbs ups, that'll let me know that it's something you'd like to see in a future video. Stay tuned for the next one. Cheers, friends.